quantum systems. This is the fourth talk in the quantum science and technology webinar series. We have with us Dr. Sudha Madam, Dr. Chandrasekhar, Dr. Girija, Dr. Shubha, and Dr. Lakshmanan, and Dr. Mohit Singh Taj, and other senior faculty as well, and also many students who have joined on both Cisco WebEx and YouTube. For all of you, welcome to this fourth talk in the webinar series. Dr. Prabhu is presently the assistant professor in the Department of Physics, in the very prestigious Indian Institute of Technology, Dharwad. Prior to joining as assistant professor, he started his illustrious career as postdoctoral research fellow in Harish Chandra Research Institute, Allahabad. Then later, he was Inspire Faculty Fellow at Harish Chandra Research Institute, Allahabad. After that, he was visiting postdoctoral fellow at the Gleb Batagin Institute of Physics, University of which is in Brazil, and also he pursued his postdoctoral fellowship at the Department of Physics at in Israel. After that, he has joined as assistant professor. Basically, Dr. Prabhu is a BSc from Government College, Kolar. Later pursued his MSc from the Department of Physics, Bangalore University. After that, completed his PhD from Kuvempu University, Karnataka. He is a recipient of many awards and honors, including excellent grading was awarded for project and the Inspire Faculty Award scheme by the Department of Science and Technology, Government of India. And he was also associate of Indian Academy of Sciences, and he was also Inspire Faculty, recipient of Inspire Faculty Award by Department of Science and Technology, Government of India. He was awarded second place for best presentation in the 27th Colloquium for Young Physicists held at Saha Institute of Nuclear Physics, Kolkata. He has completed many national projects, including multi-port quantum communication with relativistic quantum particles, then quantum information protocols with photon added and subtracted multimode continuous variable states, and also a project of Inspire faculty like quantum information theory. He has guided PhD students. He is also teaching and involved in teaching, mentoring, scientific and other activities with more than 38 research articles, of which 35 articles are published in various peer-reviewed journals. And he has taught both undergraduate and postgraduate students related to mathematical models, quantum mechanics, etc. He has mentored several undergraduate and postgraduate students for their research projects at IIT Dharwad, IIT Patna, and Harish Chandra Research Institute. He has participated in nearly 24 national and international conferences and presented research papers. He has co-organized 5 international conferences and presented seminars at Inspire, and he is also acting as a referee for various journals which publishes peer-reviewed research articles, and he was a referee for Swiss National Research Fund, and also, as I mentioned earlier, he is also associate of Indian Academy of Sciences, Bangalore from 2015 to 2018. He is also a life member of Indian Physics Association, Mumbai. It is very brief introduction. I request Dr. Prabhu to deliver his talk. The topic: a few things about quantum systems. Over to you for your presentation, Doctor.
Thanks a lot, Dr. Ramesh. So it is my greatest pleasure to be here on this platform. I would like to take this opportunity to express my gratitude for this opportunity to the Karnataka State Science and Technology Academy for this opportunity, especially Ramesh sir. So he was the one who made this possible. I request, since this is kind of a pedagogical talk that I am planned, keeping in view of the students being here in this platform. So I request everybody, if anybody has any doubt, clarification, couldn't understand something in in the way I am presenting, maybe you can just stop me and then try to interact with me and then try to get along with me. So this is a kind of a quantum mechanics first instant course, but how one can take such a course on quantum mechanics towards the quantum information is something that I am trying here. So please feel free to put your this comment in the chat section, or you can raise your hand, or you can just unmute and then just say, excuse me, I have a question, so that we can discuss all along while going through the slides or the talk. Is that fine? So am I clearly audible, sir? Ramesh sir, can you please confirm to me?
Yes, sir. Yes, sir.
Okay, great. Thank you very much. So, yeah, I am from IIT Dharwad. If you are wondering where this IIT Dharwad is present, here is a slide. We are, as you can see, the dot will represent the place where the Dharwad is present, and this is how the Dharwad looks like. And Dharwad is a very nice city to be in the to live, as well as it has very rich cultural condensation of the cultural activities in Dharwad. So you name the classical devices in the musical instruments, experts are available here, like super duper experts are here. So I recently came to know that 4 Gnanapita awardees of Karnataka out of 8 have roots in Dharwad. So, and when it comes to Dharwad, if the city is here, then the campus, IIT campus is just located outskirts of the city. From city, like maybe 10, 15 minutes drive or 15 to 20 minutes drive. So this is our campus. It looks like a pen nib. So, yeah, so since this is a very new campus, actually just got inaugurated 2 years back, so we can see that the buildings are here. So hostels, which houses almost each hostel houses 1,200 students. We have 2 hostels of that kind, and then we have a knowledge research resources and data science, where we have computer lab, library, kind of a setup, and then this is where our lectures will be held. This is a building which at any moment 3,500 students can sit. In any given moment, 3,500 students can be made to sit in these different lecture halls, and then lectures can be held. So this is a bird eye view of the entire campus. So we have admin block here, CLT here, knowledge center here, and then these two are admin blocks, academic blocks, where we are sitting. I am sitting of course somewhere here, and then we have hostel. So very nice view of the entire campus from here. And then we have a lot of facilities also available. So when it comes to students, I think I should advertise here, like we have really gone up to the level of Olympic standards to set up anything that is required for the benefit of the students, sports activities, and many other things. What about the new thing that is happening in IIT Dharwad is like we are opening MSc admissions for MSc from the next year. Actually, if you want to get into MSc program of IIT, you have to clear a joint admission for master's examination JAM. So you can look into the JAM website or you can go to our website and then look into this place where like what kind of programs that we run and things like that. So we have BTech in engineering physics, if I consider only physics side, and then we have BSMS in with physics major, MSc in physics, and then we have PhD program in physics. So if there are any students who are graduating, just you can look into the various admission pages that are available in our institute, and then try to get get an opportunity, try to get an opportunity to get into an IIT, so that you can feel what IITs are and then how they are different from other conventional institutions. So this is a small advertisement that I planned because our institute is new, and then not many people would know what it is and then why IIT means. It carries so much weightage to be in IIT and things like that. So that's kind of advertisement that I just planned for 2 minutes. So now I will come to my seminar. I am going to tell you a story. I do not bother about being fully informal. So that's why I request you all, if any confusion, any clarification, just ask me without hesitation at any point. So if there is a classical object moving, how do you get the state of the classical object? Is there any equation that I can write such a way that if I know that equation, I can get anything, any information or any physical quantity can be evaluated using that equation. Okay. For example, if I travel from Dharwad to Bangalore, okay, in a car, then I can just look for the car. Okay, so at any given moment, if I want to know what is the position of the car or how far I have traveled or how much more I have to travel, such information is required, then I have to put a coordinate system, right? I have to, like even in the Google map, it will always keep origin as the Dharwad and then put me towards the give me a path towards the Bangalore, right? So now if I put, like, what does Google does? Google actually is putting a coordinate system for that car with respect to that particular origin, right? Basically, this is a very easy thing by writing the R vector, that is a position vector corresponding to the car, you can get to know about the position. Once you know the position vector corresponding to the car, and then you can just evaluate what is the amount of time you have completed to go from one place to middle, somewhere near to Chitradurga, or somewhere near to Davangere or any other place that comes all along the um, the PB road or the direction towards the Dharwad. So you can calculate quantities like velocity, speed, or acceleration, and so on, right? So ultimately, if you know the force that is acted on the car, by knowing the mass and acceleration of the car, you know force acting on the car as well. Once you know the force, it is basically your Newton's law of equation of motion, right? F is equal to ma, which gives you equation of motion of a classical object. Okay, car. Instead of car, if you want to bus, you can take, or if you want something else, you can take. No harm, but the same set of equations will govern you this particular quantities. So now, once you know this equation of motion, okay, so then you can work out any given quantity that is required to be evaluated using this particular equation. right? So for example, if you want momentum, you can work, torque you can work out, work you can work out, energy you can work out, friction, circular motion of that particular path of travel that you are taking, and then action of gravity in that place, or difference in gravity that is acting on the car near the Dharwad or Bangalore, and then a projectile. What is the projectile? If I consider overall motion of the from Dharwad to Bangalore, what should be the projectile motion and things like that. So like you can work out in any way possible all the quantities that you name, right? So the only thing that is required here is your state of the classical system, which is your position vector. Okay, so if you know the position of any classical object, you can, if you can write an equation for that one, you can evaluate plethora of physical quantities. Okay, so now if I have such a classical object and if I want to make some measurement in the laboratory, how can we do? So for this, I will take an help from Feynman's lecture. Okay, so here is a setup where I have a source of my classical object, which is a gun, which is very bad gun basically, because when it fires in random direction. Okay, and then I have a wall here which has two holes. These two holes are placed sufficiently large enough so that a certain number of bullets will pass through these particular holes. And once they pass through these holes, they are collected in some backstop arrangement, maybe a sandbags or any other material on which these bullets can lodge after getting deviated from the holes or passing through the holes. Okay. Now, what I will do is that I will cleverly close one of the hole, and then ask the gun, like I will fire the gun, say 10,000 times. So 10,000 bullets are emitted, and then certain number of bullets will come through the hole one, okay, because there is only one hole that is available. So when it comes, the distribution of the bullets are captured by this particular graph. Okay, so you have a certain distribution that is given by this particular curve. Okay, now I will do the same thing by opening the second slit and closing the first slit. If I do that one again, I will get a certain number of bullets scattered along this particular backstop. And if you look into the number of bullets in every inch of this backstop and then try to calculate what is the number of bullets that have come here, then you have this particular curve that is created. Okay, so now fine. So I have two curves for two different holes. When they are open, what is the distribution that I get? So now what I will do is that I will open both of them together. Okay, so once I open both of them together, then the bullets can come in either way, so that they will get lodged in this backstop at random places. When you study the number of bullets that have come across this particular backstop, then you will see that there is a peak in the middle and then a gradual decrease on both sides. Number of bullets that will be coming to this one. So this is a observation that if you know how the bullet goes and then passes through these slits, you can predict with what velocity the gun bullet went through the slit 1 or slit 2, and then therefore and what angle it deviated and things like that. You can even predict the future of this particular bullet. Okay, there are a lot of information that one can get by knowing the path of the bullet and the many classical quantities that are that can be obtained for describing the bullet. Okay, so now if you instead of so now you can see that the bullets are particles, so there is no any other way of description for the bullets that are fired from the gun. So now what I will do is that I will take the wave. Okay, what I will do is that I'll take a clean, small water source where the water is level to the kind of a stagnant level. And then I will put a mechanical source in such a way that this mechanical source will always oscillate to certain particular frequency up and down, so that ripples are created in the on the surface of the water. And these ripples have same amount of amplitude, and hence they when they move away from this particular mechanical oscillating source, or the wave fronts that are generated, they will go towards the doubles to a particular stop which has two holes in it. And after passing through these two holes, there are secondary wavelets that has been created. Okay, and they will pass in the direction of the detector. So the detector can be some particular kind of a mechanism which can detect whether the wavefront has reached that particular place or not. Or you can even see it and then predict it. So now again, if I do the um, I repeat the same procedure of blocking the second slit, I will see what will happen to the wavefront. Okay, the secondary wavefront that passes through the slit one, and they will reach this particular detector. Okay, and then we have this particular intensity plot that we will get. Similarly, when I close the first slit and open up the second slit, okay, so then we get the intensity curve, that is the number, the kind of wave, the number of waves that will be detected at this point will be highest for this particular point, and hence we have a intensity curve like this. Okay, now fine, I will do the same mechanism. I will just open both of them, and then I will allow the first primary wavefront to hit these two slits open slits together, and because of their coherence, they both the slits will have generate these secondary wavelets, and these secondary wavelets will interfere in between in such a way that there is a interference pattern that is recorded, kind of a recorded on the intensity of wavefronts that will reach this particular detector. Okay, so hence we have an interference pattern. So when it is a particle, we have a distribution of this kind. This is basically the deviation of the bullets with respect to that particular slits, in such a way that there is a maximum number of bullets that are accumulated in the center, and as you go away from the center on both sides, the number of bullets are less, and hence I have a particle-like behavior. This is obviously the kind of thing that will happen, because here if you see both the curves, they are adding up with respect to the thing, with respect to the number of bullets that are coming, and hence we get resultant curve to be just addition of these two. But here, when I have this kind of beam, it is not just addition. There are, since it is an interference, there are some primary primary maximums and secondary maximas that appear in the intensity curve of the final outcome when you have two slits. So this is what is expected even when you write your equations for the two wavefront, like one source, and then it becoming two wavefronts, and then if you try to write the equations which govern this interference pattern, you will end up in describing this particular phenomena mathematically. So now even this the occurrence of the interference will tell us that the what we played around, that what is the source of my classical object is a source of which produces wavefront. So therefore this phenomena will clarify or identify the occurrence of interference among the particles that are generated. Okay, so this is how one can make an observation on the classical objects without any ambiguities. There is no any like a hidden agendas here or anything. Even at home, you can prepare such an object, such an experiment, and then you can identify them. But what with respect to quantum states? So when it comes to quantum systems, you know that quantum systems are very atomic in size, and they come in. They cannot be detected in any of the classical objects that we use, like our eyes cannot detect them, or there is no means of directly detecting them. So in that case, how do I get the state of the quantum system? In the classical mechanics, we have quantum state to be as the position vector of the position vector. But what is that equivalent position vector in the quantum mechanics for the quantum systems? When we have such a question, how do we address them? So when we seek such question, we enter into the quantum world, which I hope all of you have got exposure to, okay, because you know that the quantum particles have dual nature. Okay, they can behave as both particle as well as waves. That is the first thing that you will encounter, right? De Broglie wavelength. You calculated the wavelength of a quantum particle, and then you connected that one, right? So with respect to the momentum and the Planck's constant, which is very small in its dimensionality. So once you have the dual nature established, then you saw that there are some complementarity quantities which come in pairs, and these pairs cannot be detected together, which led to your uncertainty principle. Okay, so then comes the wave function. You defined a wave function. Schrodinger defined the wave function of wave function, and then he gave a equation of motion for that wave using that wave equation. Okay, by solving this Schrodinger equation, you will get the solution of the particle in the form of a wave function, and this is where everything started. Okay, what does this wave function give us? This wave function gives us everything about the quantum system in the quantum world. It doesn't talk about pressure of the quantum particle. It doesn't talk about any other physical observable quantities that we do in the classical mechanics. There are some quantities that are only available to be described to the quantum particles. Okay, so those quantities can be extracted by knowing this particular by solving the Schrodinger equation and obtaining corresponding wave function for the given quantum system. I will not get into those mundane work of looking into the getting the wave function and things like that. I assume that you have encountered the quantum mechanics class in your regular classes, where you may have considered some physical examples, and you you may have encountered some physical examples where the quantum states are for different, like I'll come to that one. I have a question here. For which purpose we go for Young's double slit experiment? If it is a qubit representation, dark, bright, if we go to triple slit experiment, is it equitreat? Then if N slit experiment, we may go on like this. What is that way that wrong or else this is wrong way? Why? No, I haven't yet gone to the quantum particles. Please, Mr. Gururaja, you have to wait for me to get into the quantum mechanical particles. Young's double slit experiment, then I will clearly address this question. Okay, so I just described only the classical particle which I can observe even in my common detector, that is my eye. Okay, so now if I go back to the Schrodinger equation, and then if you take any physical quantity, you know how to get the Schrodinger equation. You have to find the what is the energy constraint that is there on the on a given physical quantity. Like if you have a potential of a step or well, finite well or infinite well, you know that there is some particular energy constraints. Based on those energy constraints, you will obtain the wave functions. Okay, so one such example is your infinite potential well, in which you obtained the wave functions for different energy values of the system. Okay, so you call them as this, corresponding to this one, you called the wave function to be as the ground state, corresponding to this energy, the wave function to be as the first excited state, this one, third excited state, fourth excited state, and so on. You see, I have a quantum system which has several energy levels available. Okay, and I predicted the wave function if that particular particle falls into that particular energy function or energy level. Okay, if I don't have it, it is not there. But what we do, we try to take the superposition of all the possibilities, right? We wrote this expression as the total wave function of a particle being in a infinite potential well. Okay, and with all the possibilities, like as if I am telling you that there is only one particle, it can assume only one energy. Okay, but where all it can sit in any of these energy levels. Okay, it's not like it is there everywhere. Okay, it has a probability of seeing everywhere. Okay, so now that is something that we have to emphasize here. When we are when we are looking into the total wave function of the total system, we assume that there is a probability for each and every energy level that is available in the energy level diagram of the particle, which you obtained by solving the Schrodinger equation. Okay, so by knowing this wave function, you can know anything about the system is something that we have to realize. Okay, so not only the infinite potential well, where you started like some energy E0 and then called that energy corresponding to E1, and then you call that one as the ground state. But in another case, that is in the simple harmonic oscillator, you call the lowest energy level to be as the ground state, and then you named it as some psi naught. We do this exercise depending on our convenience. We try to name them as psi 0 or psi 1 and call them as corresponding ground states. Okay, so don't get confused. It is the lowest energy level for the given quantum system, and corresponding wave function, whether it assumes n is equal to 0, that is principal quantum number, to be a 0 or 1. So depending on that one, we will have such a classification. Now, even in the harmonic oscillator, we have a particle to possess certain energy, and this energy can be any one of them. Okay, and the corresponding to that particular energy, okay, there is a wave function description of the particle, that is the harmonic oscillator. But I don't know, because I don't meddle with the system. I should not meddle with the system. I should not do the detecting work, but I know that there is a particle which is harmonic oscillator. Therefore, I have to write a wave function for that. So for that sake of writing the wave function for the entire system, what I will do is that I will take again the superposition principle of the wave functions, and then say that for ground state there is certain C0, for first excited state there is certain C1, and so on, and then put weights for each and every wave function, and hence I connect that one to the probability. So probability will tell us the collapse of probability, which can happen only with a measurement, okay, will allow us to fix that particular quantum state to be in a given energy level. Without that, we have this complete form. But if I know what is the energy, then I know corresponding wave function, and this expansion will just collapse to that particular wave function. Okay, it's not like every day, like when I create a quantum system, all are possible. Yes, it is all are possible, but when you sneak peek into the system, there is only one which will reveal one wave function. Any one of them, one of these will reveal themselves as the measurement outcome, and not all of them. Okay, so this is something that we have to keep in mind always when we are trying to understand the wave function. Wave function is one of the possible states that are available for the quantum system in a given energy level diagram of that system, whether it is a harmonic oscillator or infinite potential well or finite potential well, step, whatever you say, barrier, all those things. But this is what I want to try to emphasize here. Okay, I will take it as a launch pad for my further discussions, and if there is any clarification that is required at this point, please let me know. Okay, so since I didn't see any clarifications requirements, so I will go ahead. Now, I will just go to the Dirac bracket notion. Yes, Ananta. So I am actually going to do this exercise, whatever you are telling. So I'm going to start with single level system, and then 2-level system and 3-level system. Thanks for that input. So now I will go to the Dirac bracket notion. So I'm extremely sorry if there is somebody who has not come across this one. Just understand there is a one-line kickstart here. Just write the wave function in this way. There is a vertical line, and then there is a angle here. So within that one, if you write a wave function, that is get. And if you want a complex of this one, you write a notion like this, which is this is what is the Dirac bracket notion. Okay, if you know these two, you can hang on to that one, and then we can work out for this seminar. Okay, so now I have a complete this is my total function. Okay, now I have a very bad this one experimental setup, which always puts my simple harmonic oscillator into the ground state. Okay, so therefore always my wave function is psi naught. Okay, so psi naught, if you want to know psi naught, then you have to go to the Kenneth Crane book or any other modern physics books or quantum mechanics one books, where it will show you the exact picture of the wave function. Okay, so now if I have a quantum source, and then if always it keeps on giving you the same energy level energy content, and then that will always reveal only the one wave function. Okay, and since it is a only one function, I can put it into a vector space which is defined, which has only one element. Okay, so which is not interesting for me. I will go hire somebody else or get something better equipment, and then try to generate a 2-level system. Okay, so assume that out of all the n oscillating energy levels that are available for you, assume there are ground state and first excited states are the two things that are available. But you can go with any possible. If you have a good experimental setup, you can choose any 2 levels at any energy level. If you want 123, 124 energy levels, take it. corresponding wave functions you can work out using the Hermite polynomial solutions of the harmonic oscillator, and then you can write the equation wave functions, you know the energy, you can play around with it. But let's start in a simple way. So I will consider n is equal to 0 and then n is equal to 1. That is ground state and first excited state. If I take these two energy levels and write the total wave function, the total wave function is n is equal to 0 and then n is equal to 1, and that is I is equal to 0 and I is equal to 1. So therefore, I have two terms that are coming. So I have a probability of a particle, my harmonic oscillator, having the wave function to be as psi 0 as given by C naught square. It's a probability. Okay, and we have a probability of psi 1, C1, in which this particular wave function, the harmonic oscillator will be in the psi 1. Okay, so there are two possible wave functions and no more. I am not talking about all the other energy possibilities are there, but I am just for the sake of my money constraint and this one, I just took only two level system. So therefore I just am playing around with it. So now you know that this is the probability for the particle in the ground state, and this is the probability, this will carry the probability for the particle in harmonic oscillator in the first excited state. So therefore the total probability should be always 1. And note here, there are two wave functions. Okay, and these two wave functions are the only two vectors that are present in my Hilbert space. So therefore, I call this vector space as the two-dimensional vector space. Okay, so now I will invest more money and then I will try to get a 3-level system. So I have fine-tuned, like I have replaced my laser light, and then my atomic system is same. So, but I took a better laser light so that I can incorporate energy injection to the electrons in an atom in such a way that I can play with the 3 energy levels. That's what it means. Okay, so I have laser lights which can play around with these corresponding energy level differences. So therefore, I have 3 energy states are readily available for me to do some exercises. So here, if I have such a system, then I have 3 levels: psi naught, psi 1, psi 2. That is ground state, first excited state, and second excited state available for us. And each of them will carry a probability of C0 square, C1 square, C2 square. That means now we have a 3-level systems. Okay, so hence, if you just see these 3 wave functions, that means that they are kind of the only 3 wave functions in a given Hilbert space, and Hilbert space is basically a vector space with dual condition. So therefore I have H3. Okay, now you see, if I make any one of them 0, okay, if I set any one of them as 0, then I will go back to the 2-qubit system. That means if I set the center one 0, that means I will not tune though it is available, I will not tune my laser so that anything will happen between ground state and first excited state, and then third excited state and first excited state. It's only whatever the thing that will happen between will be only between these two energy levels. That is the ground and second excited state. Then I have again a qubit system. I'll go back to the Hilbert space of dimension 2. Okay, in this way we can play around with the system in the a single atomic quantum system or any other quantum system which has such energy levels available for you. Okay, you can keep on doing like you invest more money, you get more lasers, fine tune them in such a way that you can do the excitation de-excitations among 4 energy levels. Then you do it. So you have C0 square, C1 square, C2 square, C3 square available. So see, in classical system, we don't have such a notion at all. We have a bullet, fine. It is a like a point particle. It went through the wall 1, hole 2 in an n-stabilized state experiment, and then I have the result. Only I have to worry about is the energy, the velocity, and then angles. If I know those two, then I can play around with, I can know what is the final outcome on this. But now, you see, I'm tuning is laser lights in such a way that there is a transition between all the energy levels, okay, within these 4 energy levels, okay. But I am not doing any measurement. I'm not doing any kind of interference with the system. All these 4 energy levels can get populated. Okay, or if I send one particular pulse of laser, then a transition can occur between any of these 2 energy levels, or it may go from one like this, hop from one place to another place. There is no constraint, but these 4 energy levels are there. Okay, and if you try to make a measurement, then that particle will click in any one of them. If you don't make a measurement, then it is possible that there is probability of getting ground state wave function, first excited state wave function, second excited state wave function, and third excited state wave function. Okay, so therefore, if I have a system which has certain superposition contained in the wave function, which is basically my state of the system, then how do we observe? What can we interpret on the observation phenomenon? Here, I just try to reveal some things like the way our friend Ananta has given in the chart. Okay, so if I have a 2-level system, okay, so then I can replace this psi naught by 0 and then psi 1 by 1, which is basically a kind of orthonormal vectors. You see in classical language also, if I have a position vector of a particle in 2 dimension, I do have a orthonormality between the unit vectors. If there are 2 same unit vectors, then if you take a dot product, that will give rise to 1. And if there are 2 different wave unit vectors, then it will give rise to 0. Because dot product will come with a trigonometric function and appropriate angles, because it should be perpendicular. So therefore, you know how to get this one. You see, similar analogous thing is happening over here. Okay, so we have zeros and ones replacing the psi 0 and psi 1. That is, if in a 2-level system, as I told you, this 2-level system, there is no constraint that it should be ground state and first excited state. It can be any level in a given quantum system, but you have a laser signal which will tune only to that particular energy levels. Okay, whereas all other energy levels are present, probability is there, but they cannot be populated because my laser light that shine on the atomic system the quantum system is tuning between only these 2 energy levels. So now, again, you can see from this definition of Kronecker delta, if A and B are same, then I will get 1, and A and B are different, then I will get 0. That's why we have a unit vector equivalence, and this is here also we call this one as some basis, okay, in the vector analysis language. So now we replace these 2 available wave functions to be with zeros and ones and call them as the basis of the Hilbert space. Basically, if I have a Hilbert space, okay, there are n number of atoms at the dimension, like there will be n allowed energy wave functions. Okay, all of them are H2. That is, they all can be written in the form of a 2 superposition, 2-term superposition, C0 0 plus C1 1. So in this one, there is a 0, there is a 1. So there is a 0 and there is a 1. Okay. All other wave functions are also possible in the given Hilbert space of dimension 2, but all of them should be expressed in these two. Then only they form a complete set of the Hilbert space. Okay, so since I can express any other point in the linear combination of these two, I can create any, I can go from, I can go to any, I can prepare any two-level systems using these 2, 0, and 1. Okay. Now, if you go to three-level system, it is the same. But now I have three-dimensional Hilbert space. So therefore, three basis vectors should be there. And these three basis vectors can be used to generate any 3-qubit system. Okay. So that's why these things are called, these particular states of this kind are called quitrits. So here also, as you can see, there is a XX, YY, ZZ in the three-dimensional Hilbert space. If you take the vector notion, you have normalization and then orthogonality. Same thing will happen here also. If you take an inner product between 0, 0, it is 1. Inner product between 2, 2, it is 1. So this will give you 1. If you take any other 0 with any other terms, any other vectors, the unit vectors, you will end up with getting, oops, you will end up in getting 0. Okay, I wrote here wrong, so just be mindful here. So this should be 1, and if you take any other two combinations, like then you get a orthogonal set of vectors notions, and then you will have a 0. I hope this makes a sense of what is the meaning of writing the basis here. So basis is basically in any given Hilbert space, there will be basis, okay, a set of vectors which are used to represent any other given point in that Hilbert space, which is basically another 3-qubit state. Okay, so now if I have such system, so we do have labeling to such systems. Okay, so if I have only two-level systems, quantum system, then I call such systems, such a states to be as the qubits, three-level systems as quitrits, and then four-level systems as why is it? So Q cards, and then we go up to the D level system. So you can keep on continuing naming in that way. Okay, so I hope it is clear that when a quantum system comes, it can come in any of these energy level, any of this Hilbert space. It can be in a wave function belonging to any one of these Hilberts. And please note this one. This is a quantum state. Whatever the state I am writing here is the quantum state of a single quantum particle. I often experience while interviewing students for PhD program or other things. When I ask them to write a wave function for two particle system, they easily write this one. It's wrong. You should not do that one. This is a probability of finding the particle in this one or in this one, and this R can be replaced by probability of C1 square or C1 square. Okay, so therefore, all of these superpositions will represent the wave function for single particle, not for the two particle. Please do not mistake that one. Now, if I have such a system, how do I do my Young's double slit experiment in the so the best source for quantum source that I can think of, like we all can think of, is the electron gun. Okay, so this is any tungsten filament bulb that is there in our houses. So they emit electrons. Okay, so now if you take such an electron source and then put appropriate backstop detectors, wall, and then the detector is appropriate enough to get the give you the current when there is an electron hitting it and so on. See, there are some initial setups that are initial conditions that are required to do such experiments. The detailed analysis of this experiment is present in the Feynman Lectures Volume 3. Please look into it. Okay, so very minute conditions required for this experimental setups has been described in that particular book, please look into that. Okay, so now I will do the same experiment. Okay, is there a question? Nalini KB. Okay, so now since the electrons are now emitted from this particular electron gun in random directions, and these two, again, I will close the slit 2 and open the slit 1, and then try to see, try to detect what is the path that is traversed by these particular electrons, and then where they get accumulated more in at the detector. Then we get a curve of this one. Okay, where there is certain distance from the midpoint of the two slits at which the peak up occurs. Okay, same thing will happen when you have another like when you block another source and then look into the most probable place where the electron will get hit the backstop. Okay, so now we have this P1 and P2. Okay, so now if I open both of them, okay, what will you see? When I do that exercise, so the electrons usually, like our common sense will tell us that electrons are particles. So therefore, they should be treated as a particles. Then P1 plus P2 should happen, and then I should get a curve of this kind. The thing that I saw in the case of the bullets. That's the common sense will tell. Like if I ask somebody who doesn't know quantum mechanics, they easily say that, you just add the particles and then you will have this one. But we are exposed to quantum mechanics. We know that electrons are no more particles, but they are de Broglie wave particles. So they can behave like a wave as well as particle. Okay, so when I have two slits open, you get a wave-like behavior exhibited by the electrons, and hence you have a interference pattern in the outcome of in the placement of electrons in this particular backstar or the detecting range. Okay, so fine. So I do understand this one, why it behaved like a particle when I closed it, when I are closed this one, but when I open both, why it behaved like a wave. Okay, because I do understand that quantum particles are when you leave them, they will behave like a wave, and then you have a interference pattern. Fine, absolutely fine. There is no harm in this one. Now I will try to extend this particular experiment. What will I do is, yes, so in terms of the states, I try to even see how the states, why this particular interference will come. See, each electron will be in two possible states. Okay, when you fix two possible states, it should be up and down. That is obviously the orientation with respect to z direction and then my negative z direction. If you want left and right also you can consider. There are to and fro also you can consider. So three possible orientations for the spins are there. So you choose one, so up and down, or you just fix it. Okay, there is two orthogonal states, so one is 0 and then one is one state. So there are two possible states for a given electron. So therefore when this electron gun is emitting, it is leaving out n number of particles. It is spreading. So now once it comes here, when there is no any source here, these particles are coming in this particular this one. If one after the other, there is 0, the upspin, downspin, upspin, downspin, 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 upspin, downspin. A series of electrons are coming, and they get accumulated in this particular curve with this ensemble of the particles. That is upspins and downspins, and then there is an ensemble of them. Similarly, the thing will happen for the second slit also. That is also an ensemble of zeros and ones. But when you open both of them, okay, you don't know, right? You don't know whether this is up or this is down or this is, you don't have a fixation to the particular electron that is coming here or here. There is no fixation. They can be up and down. There is a probability of 0 plus 1, right? So you always get 0 plus 1 and 0 plus 1. And hence, what you end up in the final detector is ensemble of 0 plus 1 and then 0 plus 1. That is, you have a superposition of the wave functions of the each and every electrons, and hence you have a wave-like behavior, because you have a wave function that is taking the quantum mechanical particle of electron to be as the wave. Okay, so in this way you can give an explanation for this particular wave pattern of the electrons and the particle pattern of the electrons when two single slits are closed and single slits are open. Okay, so now we have a electron interference that is occurring in that. By the way, this is not a right way to write it, but I have to give a 2-qubit notion. I am not yet ready to give that one, so therefore I am just calling this one as, since there is each and every point, okay, that you have a detector that is made up of 2 qubits. So it's not single electron, that is what you have to consider when the two slits are open. It should be a 2-qubit detector, so so that you will have the proper interference pattern here. Now, so when I extend this particular experiment by keeping a light source here, you see, I have kept a light source here so that I know which path this particular electron has traversed when each the time it goes. When I have two slits open, okay, I'll open the two slits and then I'll have a light source. And please, it's a very beautifully laid experiment. There's a lot of nitty-gritties are there in this one. Read Feynman Lectures Volume 3, this particular chapter 1. So this particular experiment has been really well described. All possibilities of decoherences are the effects. The environmental effects has been considered to describe this particular. I'm being really not good to take up in that level of explanation. I just want to try to understand in your hand, kind of a hand waving way to understand how things are happening. So now you see, when I have a detector here, even if the two slits are open, I know the detector will tell me that whether the particle came in the hole 1 or hole 2. Okay, so therefore I have a clear picture of distribution of the points, the electrons in the curve 1 and curve 2. Okay, so there is a curve 1 and then curve 2, there is a clear distinction, and when they are open, both are open, I know that there is a complete addition of the this one. That means now the electron is behaving like a particle. You see a quantum system, you see electrons, you try to observe electrons, they will collapse to some particular energy level. It will not go from here to here as 0 plus 1, rather it will be an ensemble of 0 and 1. Okay, either zeros or 1, and hence you always end up with it as seeing as a particle. So hence you have a particle-like nature when you observe the electron. You see, so same electron without this light source, that means you have no interference you are doing, no any eavesdropping you are doing, then you have a wave-like nature. But when you try to see it, you have a particle-like behavior. There is no interference in the due to the electrons. That means the electrons are no more behaving like a quantum particles, but rather like a classical particles. So what can I conclude here is that when you do a observation on the quantum system, they will reveal themselves in a particular state. When you don't do the observation, You have all the probabilities, a bundle of probabilities of the particle being in any possible wave energy level. But as soon as you see, it will collapse to any one of them. Okay. The external influence will alter the state of the quantum system. If you want a quantum system to behave like a quantum system so that you can use it as a resource for any purpose, okay, then don't interfere with its state. Don't see them. Allow them to go as they want, as they are, and then let them do their work. If you try to see them, then the state will collapse. There is no more quantum state and you are in a loss. That's why this famous quote of a question that Einstein posed to Abraham Pais, that do you really believe the moon is not there when you are not looking at it? So when I don't see the moon, it doesn't mean that moon is not there, or it is something else that is there, right? It is a classical sense of understanding. Always, Einstein had a very strong belief that we should explain quantum particles also in the classical sense. He didn't like these superpositions. He didn't like the way that we are telling. If you see, it will go to one state. If you don't see, it will be it will behave like a different. Okay, he didn't like it. That's why he was sternly opposing quantum ideas. And there were a lot of debates on between him, Schrodinger, Bohr, and many others on the way how to describe the quantum system in this one. That's a different story. One can take up in a separate session. So now I would like to give some kind of a hands-on, like how the quantum states can be handled on pen and paper, so that it will help me to understand some protocols that I do encounter in quantum information. Okay, so I will take a two-level system. Now I have replaced my psi 0 and psi 1 by 1 and 0 and 1, because these are basis states. Okay, so now you see, when I have a basis state, what I'll do is that since they are orthonormal, I'll give a matrix structure to that one. I'll call 0 as a column matrix of a 2 cross 1, and then here also column matrix of 2 cross 1. And then you can see that if you take an inner product of 0, 0, then it is just 1, 0 with 1, 0, which will give you 1. Okay, it's just a matrix multiplication. Okay, but if you take a 0 and 1, you will see that it is 1, 0 with 0, 1, which will be equal to 0. So therefore it is orthonormal. So it works well. So to call this 0 to be as 1, 0, and then this 1 to be as 0. If you want it reverse, you can do it. And then if you fix to a convention, you have to stick to that one. If you call 0, 1 as 0 and then 1, 0 as 1, no harm. But you have to fix to that one. Usually a general convention is 0, 1, 0, and then 0, 1. So now, this is a quantum state which belongs to the Hilbert space of 2, because there are 2 basis vectors defined in this for this particular state. So now, I have a state. So I can write this state as this one, because alpha into 1 and beta into 1. So therefore, when I add 0 plus 1, I will just get alpha, beta. And if you take a conjugate of that one, this is my bra notion, and then this one is ket. If somebody is new to this notion, please note this one. This is Dirac's bracket notion. A wave function is written in the form of a column matrix, and then the complex conjugate of that one is which is called as a bra is written as a row matrix. Now you can see that psi is 1, because when you multiply this psi, okay, you will get mod alpha square plus mod beta square. You know that mod alpha square plus mod beta square should be equal to 1, and hence I have inner product to be as 1. But if I take an outer product, okay, so we all define that one, we get a 2 cross 2 matrix. Okay, this outer product is a density matrix. Please note this one. There is a lot of students community which do not know what is a density matrix. So density matrix is again a state of the quantum system. You can write the state in the form of a wave function or in the density matrix. Both gives you the same description. For example, you see here mod alpha square and mod beta square. Can you see the diagonal element of this matrix? So these diagonal elements of this density matrix gives the probability of the states. Okay, so probability of the states in being in that particular eigenbasis or a vector basis. Okay, so therefore the density matrix is also a kind of a state representation. Now, this is all about a given qubit in its notion of 0 and 1. Usually 0 and 1 are called computational basis, and then so they are called computational basis because they are there are something like analogous to like our information bits of 0 and 1. So we have, this is the notion. Now I take two systems. When I take a two system, please note I want to write a wave function for both the system together. Therefore I have psi a and psi b. I am trying to write a wave function, both of them together and not individually. So I can write one way to write those two equations, those two wave functions, as like take a product like this. What is this? This is the tensor product. Okay, basically how it like if you have a two-level system, you know that there is only two-level system, you will have 0 0a and 1a, and then I have 0b and then 1b. These are the possible superposition states for the wave function, and for this one it is here like this. So therefore I can make a general two-qubit wave function psi ab, that is composite system. Composite means it should have some subsystems. Now both can be 0 0 with certain probability alpha, both can be 0 and 1 with certain probability beta, both can be 1 0 with gamma, and both can be in 1 1, that is delta. But all of them have certain probability. Okay, this is the most general way to write the two qubit system. Remember here, I am writing this notion. It should be understood what it means. So therefore, I will try to write this product structure like a rho A into rho B. Usually we do not write tensor product and then keep it clumsy. We do generally write like this. Basically here 0 A 0 B means that I have 0 A tensor product 0 B. This is what you mean. We do not want to make a lengthy notions, but a shorter notion is this one writing. But remember, if I write somewhere 0 0 or 0 1, it means that the first place of the ket notion is for the particle 1. Always it is for the particle 1. The second position of the particle in a given notion is for the particle 2. If there is three particle system, then the place is corresponding to first qubit, second qubit, and third qubit, or first level, second level, first particle, second particle, and third particle. Please note this one. So now, so since they both are zeros and then they both in the matrix, we don't have a distinction of the basis vector. So therefore I will write like this. So to do this multiplication, you have to take each element of the first matrix and then multiply the entire matrix over there. Okay. So 1 into 1 0. So therefore I have this one giving me this as the output, and the 0 is to entire matrix will give me this one. So it is a matrix tensor matrix multiplication. Okay, so you have to take a particles first element of the matrix and then multiply the entire B block, the B matrix, and then take second element and then multiply entire B matrix. So therefore you will get a 4 cross 1 vector. This is what is the basis vector in the two-dimensional Hilbert space. Here, this is a basis vector for the qubit, that is that is for the 4-dimensional, the 2 cross 2-dimensional Hilbert. This is for the Hilbert space 2, but this is the basis vector for H2 tensor H2. I should not write H4. H4 is for the other one. So we have this particular composite Hilbert space, which is given by this one. Okay, so we have 2 qubit system represented like this. Now, if you want to write a density matrix, corresponding density matrix, you see you can write rho AB, which is psi AB, outer product psi AB, and then you can see that you have a density matrix structure as well. Either this one is a state or this one is a state. Either one can be used. You see, the probabilities will always be with respect to diagonal here in the matrix, and then here you will have the corresponding weightages. So therefore, you can write a composite system by looking into the what is the individual state vectors, and then take a direct product, and then do the tensor product, and then do the multiplications. Now, if I have a 2 qubit system, is it the only way to write psi A and psi B in the form of a tensor product is the question. Okay, if we write, okay, so then we call such states to be as the product states, or separable states, or unentangled states. Okay, usually such definitions is carried for the pure states. Pure states means that the trace of rho should be 1. Always the density matrix should be positive definite. That is, if you calculate the eigenvalues of the density matrix, all the eigenvalues, corresponding eigenvalues will be positive definite. Okay, and then rho square will be rho, and trace of rho square and trace of rho will be equal to 1. Okay, so now if you take a pure, if you want a pure state, then the entire universe is the only possible ideal pure state. Okay, you cannot find any other pure states than the entire universe's state. Okay, and when you write a pure state wave function, you know everything about this system. Okay, when I write like this, you know everything about that particular system and composite system. Okay, but if you cannot write in the form of a product, okay, see, for example, I have 0, 0 plus 1, plus or minus 1, 1. You cannot write this one as individual psi A as something, and psi B as some combination of zeros and ones. Okay, since I cannot write, there is no way I can express this one as the in the form of a product state. That is the state, individual subsystem states you consider, and then put a direct product or the tensor product. That is not possible. If such systems comes into your kind notice, please treat them as the non-product states or non-separable states or entangled states. The opposite words has to be used. And product state is something that we use only for in case of the pure states, which has these 2 special conditions satisfying. But if you go to a yeah, so I want to tell one more thing here. So if I have this kind of a states generated in the lab, okay, say for example, we both came together at some past together today, and then we generated 2 qubit state. You took 1 qubit with you, I took 1 qubit with me, and tomorrow when I come, okay, I'm curious. I don't know what is the state that you have. Okay, I'm curious. What I will do is that I don't know where you are even there. You may be at the end of the opposite end of the universe. Okay, if I do a measurement, I know what is the total system. Like when we both sat together and created a 2 qubit system, we both know what is the 2 qubits that 2 qubit state that has been generated. For example, this one. Okay, I know that if I have 0, you will also have 0. If I have 1, I know that you also have 1. right? So now, if I make it, I am being cunning and very curious about what is the state that I have. I want to know whether I have 0 or 1, and I want to also know about what you have. So what I will do is that I will make a measurement. If 1 comes, you are untouched, you are somewhere where I human cannot go and then tell you, but I already know that what is your state, what is your particle state. It is also in the 1. You see, information about your particle is passed on to me with the speed which is greater than speed of light. You understand the context here? Like, we both created. We know that if I am 0, you are also 0. If I am 1, you are also 1. We took our particles outside, but I don't know till I open the lid and then make a measurement. I don't know what is my state. Okay. Once I know what is my state, I immediately reveal without disturbing your particle. I know that what is your particle. Therefore, information has traveled to me from your place to me without any delay. That's why when entanglement was proposed, Einstein again called this one as a spooky action at a distance. It spooked him. Okay, so that's why we have that famous quote called spook. And in case of mixed states are the ones where we have these 2 additional conditions coming, like say rho square will never be equal to rho, and then trace rho square will be always less than or equal to 1. When I have a mixed state, again, if I know the individual subsystems which occurs with certain probabilities, then I have a separable system or an entangled state. And if I cannot know the individual subsystems, I know everything. The such systems are called entangled systems or non-separable states. The another a line of definition, if you do not want to use the mathematical language, you can define the entanglement as if I have a composite system, okay, I have a composite system in which I know individually what is the state of the system, then such states are unentangled. But if I have a composite system where I don't know what state is each of the particle, then I can call that one as a entangled state. To know the actual state, you have to make a measurement on the entangled state. When you make a measurement on the entangled state, there is no more original entangled state, but some class you have disturbed the state, and hence there is no actual behavior, actual properties of the state is not captured. Okay, so by the way, there is a protocol called LOCC operation, which will allow us to create such systems. Okay, I'll not get into that one. Maybe I can say that if a state can be prepared by LOCC operation, then we call such states as separable states or unentangled states. If we cannot prepare them, then we have separable state, entangled states and the entangled states. So LOCC is basically a kind of a protocol in which you see there are two parties who are sharing this particular quantum state. Okay, so they are sharing and they have multiple copies of them. So when they came together, they made billions of particles, and then they took the first person took one particle, and second person took the second particle, but they are all identical to each other. Okay, so because they have same source that has created the state, so therefore the condition is that they have identical source. So the first person with curiosity, she makes a measurement on a particle, and then whatever the measurement outcome she gets, okay, she gets some particular output like this. And it occurs with certain probability. Oh, sorry, this should be P's. So probabilities. Okay, this is not state row A. Somewhere I think cut and paste error here. Now when I make a measurement with certain probability, okay, so say there is this particular state will occur with certain probability, and the measurement outcome is she will call him and then tell that, okay, see, for this particular measurement, 1 3 4 2 4 measurement, I got this particular state, and then immediately what he does another measurement and then reveals what is his measurement outcome, and hence both of them know what is their individual states which occurred with certain probability. And remember, this is a 2-qubit state. It occurs like a 0, 0 plus 1, 1 kind of a state, right? So it has certain probability of 0, 0, 1, 1 kind of it. So now they keep repeating this cycle for long, 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 because they have a billion copies, they can keep on repeating. So therefore, if they can create a state using of this kind, where individual subsystems are known to each of them, then we have LOCC operation successfully conducted, where I know subsystems to the fullest extent. I know everything about the subsystems, and hence the composite system is a unentangled state. But you cannot do such a protocol, then you will end up with a entangled state. Okay, so now I will just try to give a glimpse like what is the complexity that is there in entanglement, and then try to, I want to leave you with a kind of a notion like how what is not only defining the entanglement, what are the other intricacies that are there in entanglement in the when we have multi-partite system. See, entanglement comes in different ways: 2-qubit, 3-qubit, 4-qubit, multi-qubit, and so on. Okay, so when I talk about a subsystem, where should I put the line? Okay, there are variety of states. Where should I put? Should I make it by two separate like unequal divisions or equal divisions? Or can I make a three divisions and then check entanglement between 1, 2, 3 subsystems? Or should I consider whole as a system which is called genuine multipartite system, where entanglement can be quantified using certain quantities? Okay, so for each of such different scenarios that you come across in multipartite scenario, you have to devise a definition for that. You see, if I want to if I want to calculate the pressure of that is present in the overhead tank, and then a pressure in my of the liquid in my coffee mug, okay, both have same pressure equation, PV is equal to nRT, right? You solve that one, you get the pressure equation, right? But I have a quantum systems which comes in various colors, various ways, but I have to also consider how do I split them so that I can talk about the entanglement between which subsystems. So therefore, entanglement variation will also be like quantification is also a challenging task. Okay, so for 2-qubit system we can handle in a more efficient way. I think somebody or the other would have been told, will tell, or would have already gave you the notion of von Neumann entropy and concurrence, which quantifies the entanglement. Always our measure should, a good measure of entanglement is such a one that it should be 0 for unentangled state, and it should be 1 for maximally entangled state, and it should be some intermediate values for intermediate entanglement present in the system. Okay, I think I will stop here because of the time constraint that we have. So if there are any questions, I would like to take up the questions here.
Thank you, sir. I request participants to post their questions in the chat box or in the Q&A section, or they can raise their virtual hand so that I can unmute them, or you yourself can unmute and speak to sir directly and ask your query.
Yes, Yuvraj, please unmute yourself and then pose your question, please.
Dr. Prabhu, really it was a very insightful and scholastic talk. I'm sure many students would be highly benefited by your talk. On behalf of Karnataka Science and Technology Academy, thank you very much for your lucid and insightful talk on a few things about quantum systems. I'm sure there will be few questions by faculty and students. Are there any questions?
No,
Thanks
sir,
a
in the
lot
chat
for the
box.
opportunity, sir. So it was, I hope I could disseminate some amount of information to the young students who,
Yeah.
who could listen to me. And if anybody has any question, do not hesitate. Always go to IIT Dharwad website, find my link, and then you can find my email over there. And actually, I'm also flashing it right away. So you can write to me directly, and then I can discuss with you over the email.
Doctor, Mr. Gururaj has a question on chat
Yeah,
box.
so for which purpose we go for Young's double slit experiment? Like just like I want to give you one scenario where the how measurement can be exploited. You see, I just wanted with this experimental setup, Young's double slit experiment on the electron. My ultimate goal was to go to electron. Okay, so you can do multi-slit experiments as well, but why complicate when I want to tell in the first place? Okay, so people have done like a 3-slit experiments, for example, our own RRI, professor from RRI, Professor Urvashi Sinha, she has a 3-slit experiment done. So it is possible. There is nothing wrong in considering different kind of quantum systems. But once you fix a quantum system, then you have to work out the integrities. Hi, Satyajit.
Hello, Prabhu.
Hi, how are you?
Yeah, I'm good.
Yes.
Wonderful lecture. I enjoyed it very much.
Oh, thanks you.
Thank you so much for this nice lecture. Yeah, I just wanted to say my appreciation for that.
Oh, thanks a lot. Thanks a lot.
Yeah. Thank you.
With us, Professor K.S. Malesh, sir. Sir, would you like to say anything?
So thank you, sir. Thank you, Dr. Prabhu.
Hello, sir. How are you?
Started.
Nice to
Okay,
see
fine.
you, sir.
Yeah. I was out of station, so I couldn't attend the first 2 lectures. But since yesterday I'm here, you started from very basic things, and you even came to some multi-particle entanglement. Hope the students who have heard your lectures would get encouraged, and I am sure many of them will now start thinking of entering into quantum technology and other. Thank you so much for a nice lecture.
Thank you very much.
Thank you, sir. Ramesh, thank you very much.
Thank you very much, sir.
Dr. Chandrasekhar is with us. Dr. Chandru. Dr. Sudha, madam. And we have with us Dr.
Hello,
Anand.
Prabhu.
Yes, ma'am.
Nice lecture and pedagogic one that I am kind of relieved that mine too is going to be, though not as pedagogic as yours, I'm kind of heartened. Thank you.
Thanks, ma'am. Thanks a lot for your appreciation.
Dr. Anant Naik, who is also an expert committee member of KSTA. Dr.
Sir,
Anant.
I would like to ask Prabhu, sir. You have mentioned that there is a superluminal information transfer in the case of entangled states. But from the point of view of a student, anybody can ask possible question.
Oh, I really didn't wanted to go
Is
to
there any
causality,
possibility of superluminal
non-locality and these things at this level. See, we need some kind of a exposure to be given to them because localism, realism definitions they would have not heard about. So therefore, I didn't really wanted to expose to like too many things in a given time. I could have gone there. I had planned initially, but later I thought that I will stop here.
I just asked because we have this special theory of relativity in first semester of ITEP program for BSc BEd students, and they themselves have this type of questions in front of me. Then it's the time to ask such questions to use that I can have some a glimpse of. I mean, how can I tackle them in the class? That's all. That's all.
Yeah,
Nothing more
thanks
than
a lot. So yeah, I am. See, when I see such a vibrant forum now, so I would like to keep as simple as possible. So without presuming that they know much. So that's what was the idea. So I hope if causality has to be considered, then surely we have to take another session for that. So causality, non-classicality, realism, all those things has to be described, and then give the implication to the Bell's inequality and violations, and then from there we can talk about the other things.
Of
Right?
course, sir. Of course. Thank you very much, sir. It's a very good lecture from you. I will, if time permit, I will ask my students to ask questions more than
Please do so.
the
No,
class.
do not hesitate. You have my phone number. You can always call and then try to check with it.
Thank you.
Thank you, Ananta. Thank you.
Now, Dr. Yashoda is there with us, Dr. Zina. Hello, Dr. Yashoda and Dr. Zina. Hello. Okay. Okay, Doctor. Thank you very much.
Thank you for the opportunity. I hope everybody enjoyed and learned. So yeah, thank you. I wish you all the happy evening. So,
I could also pick something from your talk. I'm not very familiar with physics or quantum.
now I think we should be more careful about our report.
So on behalf of KSTA and all the participants, thank you very much. It's the fourth talk we had. First talk was by Dr. Usha Madam on Tale of Quantum Information Science. Second by Dr. H.S. Karthik on Reviving Quantumness. And the third talk was on quantum cryptography. And today we had a very good talk on quantum systems. And tomorrow, Dr. Sudha Madam will be delivering a talk on quantum science and technology, a bird's eye view on origin and development. So, Madam will be speaking something about the history of quantum science. So, I request all of you, all the participants, to join by 3:50, so that if you have any joining issues, you can resolve by 3:30 and be with us in the webinar. On behalf of KSTA, I thank all the senior faculties who have joined for this talk. Our expert committee members, Dr. Sudha, Dr. Anand, Dr. Akshata, were there with us. Thank you very much. And Dr. Girija is there. She is from BLD University, and her students, more than 80 students have joined. For all of them, thank you very much. And many senior faculties like Dr. Yashoda, Dr. K.S. Malesh sir, Dr. Shubha, Dr. Smita, Dr. Meeta, Dr. Lakshmanan, Dr. Maharajan, Dr. Kantraj, Dr. Mohisin Taj, Dr. Zina, Dr. Pantarangappa, Dr. Sangeeta. So many have joined. For all of them, thank you very much. Please encourage your students also to join for tomorrow's session. Madam will be speaking about the quantum systems. I mean, basics of quantum science and technology, which your students will understand better with today's and previous talks. So with this, I thank all of you for being with us for the last 4 days and for today also. Thank you very much. Dr. Prabhuji, thank you.
Thank you, sir. Thank you, one and all.